Throughout many years of development, experimental physics has come a long way from primitive experiments and accidental observations, for instance, Newton and his apple, to modern research, complex and costly. Nowadays, the apex of scientific evolution is experiments devised to study physics of elementary particles, their behavior, transformations, and interactions. This is the field of high-energy physics. Enabling experiments in this area required devices to be designed and built that are now generally categorized as charged particles accelerators. Such devices share a common purpose: obtaining charged high-frequency particles and registering their impacts with each other or with static targets. The result of such impacts is emergence of super-high energy concentration in a microscopic volume, and consequently birth of new particles. It is their properties that scientists study. However, despite shared purpose, accelerators are distinguished by operating principle, by how acceleration process occurs, as well as by experiment conditions and by handled particle types. In this respect, they can be compared to automobiles that are all designed for transportation, but have significant differences in design and application. All accelerators are based on particle interaction with external electric and magnetic fields. The electric field increases the particle's energy, accelerating it, whereas the magnetic field deflects it in line with the required trajectory, focuses the particle beam without modifying its energy. Generally, all accelerators can be divided into two big categories: linear ones, in which the particle beam passes through a straight accelerating section once with impact occurring at its end, and cyclic ones, where particle acceleration occurs after multiple passes of a closed curve. Let us have a quick look at some types of accelerators. For instance, a cyclotron. It has two hollow hemispheric electrodes, semi-cylinders with alternating voltage applied between them. In addition, they are placed between the poles of an electromagnet that creates a constant magnetic field. Accelerated particles are injected into the chamber's center, and field's action causes them to move inside electrode cavities. The magnetic field curves their trajectory. The particles accelerate each time they pass through the gap between the electrodes. Electrode's voltage polarity change ratio equals to particle's rate of spin. Particle energy and rotation radius are growing, and after some time the accelerated particle leaves the cyclotron. The cyclotron is the first cyclic accelerator built in the 1930s. It is used to accelerate heavy particles to relatively small engines and energies of 20 to 25 megavolts. In a betatron, acceleration is created by an electric eddy field. A cyclotron has a circular vacuum chamber in which magnetic field is created and grows in time with constant frequency of the accelerated electric field. Particles are accelerated in the chamber as they enter the accelerating field, always in resonance with the field change. Such devices are fairly powerful. The famous tubular synchrophasotron accelerated particles to energies of 10 gigavolts, which was recorded high at the time, middle of the previous century. Its magnet diameter equaled 60 meters and weighed 36,000 tons. Generator's capacity totaled 140 megawatts. However, this is by far not the limit. The famous LHC Large Hadron Collider, intended for acceleration of protons and heavy lead ions, has a circular ring's length of almost 27 kilometers. Hadron means it accelerates hadrons. Particles consist of quarks. Colliders are a particular type of accelerators in which oncoming particle beams are collided. There are about 15 of those worldwide in the US, China, Europe and Japan. The LHC is the largest and highest energy of them. It is planned to run a series of experiments in it to study such aspects as photon, hadron, collision, top quarks, and searching for supersymmetry. The speed of colliding particles in the accelerator is approaching light speed in vacuum. Acceleration occurs stage by stage. Initially, particles are accelerated in a linear accelerator, after which they are successively injected into rings of 3 synchrotrons of various diameters and finally into a large tunnel, where final acceleration in opposite direction happens until maximum energy has been reached. Then particles collide in a specific location next to the detectors. total proton collision energy in it is about 14 tera-electron volts. Kinetic energy of all hadrons in the LHC, when filled to capacity, is comparable to that of a jet airplane, although the total particle mass does not exceed a nanogram. Such energy is achieved due to colossal particle speed that approaches light speed. The tunnel is located underground at depth from 50 to 175 meters. Superconducting focusing magnets are cooled to minus 271 degrees centigrade. Such an elaborate mechanism is still in the tuning up stage. When the LHC starts operating at full capacity, it will help scientists unravel the scientific mysteries and explored before.